Welcome to the section on the naval use case. In this section, I will be showing and discussing the work that was performed at Thales for the ADMORPH project. Going back to the overview of the ADMORPH project, for the naval use case, the main challenge was to see if the ADMORPH approach could be applied to an application whose components run distributed on an embedded networked multi-node system, instead of on multiple cores on an embedded system on chip. To do this, the core body of our work was developing an adaptation mechanism that was suitable for our runtime environment. This work culminated in the demonstrator, which I will be discussing further on. This was combined with an investigation into a suitable update framework for both us as well as our ADMORPH partners, resulting in a setup that works with our demonstrator to show the ability to combine an update framework with an adaptation mechanism to achieve greater fault tolerance. Finally, we performed an evaluation of the team play coordination language in laboratory setup. I will be discussing this evaluation first. The goal was to evaluate the concepts and features of the coordination language and investigate their usability for a radar surveillance system application. However, this was not necessarily with the intent of implementing the coordination language for our use case. Initial impressions of team play were quite good, with a parallel between team play and the DSL currently in use at Thales being immediately apparent, as both languages model applications as a set of interoperating components with respective inputs and outputs. Looking at the language specification of team play, there are multiple features that pop out as interesting for Thales applications, as they might solve some of the problems that we currently face, or add very useful functionalities that our current DSL does not yet have. The first being modeling of non-functional properties. Radar surveillance systems can have quite stringent non-functional requirements, and explicitly modeling this as a property of the application and implementing mechanisms that can ensure these constraints are adhered to at runtime is an elegant solution to meet set requirements. The second, which is an extension on modeling non-functional properties, is the modeling of fault tolerance properties. Having multiple implementations of a single component with different security properties or different versions, or just the ability to use replicas, is a feature of team play that we quite like and is not yet possible with our own DSL. And lastly, modeling the state of a component as part of the design, thereby enabling relocation of components with retention of state, had already been identified previously as something that is needed for our applications, and it is something that team play also provides. So all of this begs the question, why did we not use the coordination language to implement our use case? The first reason is a difference in granularity. Team play is designed with the environment of multi-many-core heterogeneous platforms in mind, with the goal of minimizing the chance of failure in a single core and simultaneously maximizing the lifetime of the platform, whilst a typical naval radar has entire server racks of available resources, each of which has many cores, making the failure of a single core negligible. Thales' interests therefore lie in applying more redundancy on the node level. The main reason we did not use the coordination language for our use case is due to the assumptions about the nature of the components that comprise the application. Team play has been designed for components that use stream-oriented communication, whereas our radar processing applications consist of communicating state machines, with the main problem being that this would invalidate formal guarantees that come with stream-based processing. To conclude this section, even though the coordination language in its current form cannot be applied directly to model an application consisting of communicating state machines, such as those currently in use in our radar surveillance systems, there are certainly some aspects that are interesting for further exploration within the context of our development environment. Having non-functional aspects like latency requirements, security levels, or even multiple implementations of a single component as part of the design model is a concept we have already identified as something we might need, and the ADMORPH approach could certainly be used as an inspiration of how to apply this to our own environment. Especially the elegant solution to model the state of a component as part of the design is something that we would like to look into. Next, I will be showing the core body of our work, that being the demonstrator that we developed for our use case. This demonstrator serves mainly as a proof of concept for an adaptation mechanism in the runtime environment of a radar surveillance system and demonstrate that these techniques could be used in future Thales applications to solve some of the problems that we currently face. First, I want to elaborate on the software architecture of a Thales radar surveillance system, as this relates to the problems that we are trying to solve with the demonstrator. At Thales, software processes are modeled as components, which are deployed in containerized applications. Multiple containers form systems which can be used to form systems of systems. This way, components and systems can be reused in different configurations. Currently, the software processes that comprise a radar surveillance system are statically allocated and deployed by hand. This poses a high risk of hardware or software failure causing significant downtime. The main goal with the demonstrator was to mitigate this problem by dynamically allocating resources at runtime based on the current use case of the system and the available hardware resources. The first step in attaining this goal was to implement a model that the adaptation mechanism could use to discern which components should be deployed for each use case, as well as model the usage of each component and the relations between components. To do this, we selected the OSGI Requirements Capability Model, which, as the name implies, is used to model each component as a set of requirements and capabilities. Using the modeled use cases, components, and hardware, we then resolve a valid deployment of processes on available hardware using a genetic algorithm, resolver. In the base OSGI model, a capability can meet a single or any number of requirements. However, for hardware and some software, that is not always the case. For this reason, we extended the OSGI model with the concept of consumables, where capabilities, for example memory, are finite, and requirements that use such a resource consume a portion of the capability. I will now be showing a demonstration of the resolver. What you see here is a collection of simulated components and hardware. To start the resolving process, I've introduced a use case called ADMORPH Test. This use case requires component 00, and each component subsequently requires the next component in the list. I would also like to note that in real time, the demonstration I'm about to show only takes a couple of seconds. We start with the functional composition stage, where a matching capability is selected for each requirement. In this demo, 4 individuals are created per generation, but this number is configurable. As the functional composition stage progresses, we can see how the requirement of each component gets fulfilled with the capability of each subsequent component, as well as the component's hardware requirements being matched with the available hardware. After the initial population is created, we see the highest scoring individual of this generation. Each subsequent generation, the resolver will attempt to find a more optimized solution using its genetic algorithm, which in this case would mean a better load distribution across all available hardware, but the fitting functions that are used to score each individual are also configurable. Just now in generation 8, the resolving process increased the fitness score by adding the final piece of hardware to the deployment. The complete process takes 50 generations, but I will end the demo here since the solution is already quite optimized given the fitness functions that are currently loaded, and skipping to the end of this demonstration would show that despite some changes in component allocation, the fitness score remains the same. Using the resolver, we can dynamically redeploy our system based on the given use case. For our radar surveillance system, we deploy different types of radar processing chains. In addition, we track the available hardware in our multi-node cluster, so in the event of hardware failure, we automatically redeploy to keep the system functional with minimal user impact. I have a short demonstration of this, where we start with our radar surveillance system in standby, requiring only a few components. As we switch to the CPRTOL use case, the resolver calculates a valid allocation for the corresponding radar processing chains, which are then deployed alongside the already running components. Switching between different types of patrol functions identically, with the adaptation mechanism starting and stopping processing chain components as needed. Although the adaptation mechanism already provides a greater means of fault tolerance compared to our current runtime environment, we still had a potential problem. In the event that enough hardware fails, it would mean that there are no longer enough resources available to deploy our system, therefore still limiting the amount of hardware faults that are allowed to occur by a significant margin. To mitigate this problem, we came up with the solution of explicitly modeling degraded versions of components. As this example shows, once a failure results in the system no longer being allocatable in the normal configuration, we can instead deploy a low-performance version of components, which means that although the processing chain is not running at full capacity, it can at least still operate despite the lower amount of available hardware. This next demonstration shows the concept in action. Here we see an optimally deployed use case, where each of the components of the surface surveillance chain are using a high-performance version. As I start causing hardware to fail, the adaptation mechanism will gradually start deploying low-performance versions of components instead, in order to maintain a usable system despite the decrease in available hardware. At this point, we still have a decent amount of hardware available, and most of the deployed surface surveillance components are still running the high-performance version. To force the adaptation mechanism to start using low performance components, I have caused some more hardware to fail, and you will be able to see how even though only half of the original amount of hardware remains, we can still keep the system operational using this technique, with the server surveillance chain having almost fully moved over to low performance components. So by implementing an adaptation mechanism that is compatible with our runtime environment, we are now able to dynamically deploy our applications based on use cases. We can adapt to hardware faults both by redeploying our applications and instantiating degraded versions of components if required. Future work relating to this adaptation mechanism comes mainly in the form of implementing the features and concepts that were discussed during the coordination language evaluation, namely modeling non-functional requirements to be able to use the resolver to compute a deployment that meets those requirements, and retaining component state, since that is currently lost on each redeployment. Finally, I'm now going to discuss our work on an update framework that could be used in combination with other ADMORPH mechanisms to improve fault tolerance and resilience against attacks. We opted not to develop such a mechanism ourselves, but instead performed a best-of-class investigation into existing tools and frameworks based on the criteria shown on the slide. From this investigation, we selected Mender as a commercial off-the-shelf update solution, which meets all our security criteria, but is also customizable enough to be used in our infrastructure as well as those of our ADMORPH partners. To demonstrate the update framework working in conjunction with other ADMORPH mechanisms, I've introduced a bug in the ship state component of our adaptation mechanism demonstrator, causing it to only produce pitch data. Once I have a fix for the issue, I combine the container image of the updated component with two changelog files. The first is for the ship state component, which describes the requirements and capabilities of the updated version of the component. And the second contains a new use case to demonstrate the introduction of new functionality using this method. These are compiled in a so-called update artifact, which is uploaded to the server of the update framework. The server of Mender comes with a nifty GUI that allows one to monitor all their connected devices and create deployments for new updates. Using the generated update artifact, I will start a new deployment for the update containing the fix for the ship state component, and it will be set up to deploy momentarily. On the client side, the client will periodically poll the server for new updates. Once an update is available for download, the client will check in with the adaptation mechanism to see whether the application is in a state where updating is allowed. In this case, the update is allowed to continue, and the client will now download and install the update. After installing, the adaptation mechanism will immediately replace the old component with the updated one, as you can see here, since the ship state component is now using version 1.0.1. This fixes the issue with almost zero downtime for the user. We also have the new use case off immediately available for use as well. Concluding the section on the update framework, by using an off-the-shelf solution, we can improve resilience against faults and attacks by supplying secure atomic updates to remove vulnerabilities, add new features, and fix issues. The high customizability of Mender means that it can be tailored to the requirements and environments of all consortium partners, and in fact, it is already currently in use at Thales. With that, I have finished the section on the naval use case, and I would like to thank you for your attention.